Today we're going to talk about what happens when a particle with angular momentum is placed into an external magnetic field. It begins by looking at a magnetic dipole, and the prototypical dipole is a current-carrying loop, where this lowercase I is the current, A is the area enclosed by the loop, B is the external applied magnetic field, which may be at any skewed angle, and there's an important axis which is normal to the loop, which we need to talk about. Mu is the magnetic dipole moment. It equals the current in the loop times the area, and it is perpendicular to the loop. We'll just call that the z-axis, so k hat will be the axis that is normal to the loop. If you place the magnetic dipole into a magnetic field, you'll have a potential energy, which is minimized when the magnetic dipole moment aligns with that magnetic field. So when mu dot B is as large a number as it can get, that is mu and B are aligned, and then you have the minus sign to make it negative, you've got an energy minimum. That external magnetic field puts a torque on the magnetic dipole. Cross product of the dipole moment and that external magnetic field is the torque that rotates the dipole. If the magnetic field is inhomogeneous, you also get a force on the magnetic dipole. If you have a gradient in mu dot B, which you only have because B has a gradient, then there will be a force causing the dipole to move in space, not just rotate, but translate. That's an important consideration when looking at the Stern-Gerlach experiment. Now let's do something mechanical to this loop. Let's start rotating it. So if the loop is actually like a wire, so there's stuff, there's actual physical mass present where that current is, and the mass is rotating around, probably with the current. That might be how it's working. If this is a ring of charge and it's rotating, then the charge and the mass are rotating at the same rate. If the current loop is rotating, there's going to be angular momentum. So if it rotates at, we'll say, an angular speed of omega, then there will be an angular momentum for that system. So now we have a magnetic dipole moment and angular momentum, and the ratio of the two is called the Gyromagnetic Ratio, and it makes sense that they would be related through a constant. The faster a ring of charge rotates, the larger the magnetic dipole moment and the larger the angular momentum. So this is the Gyromagnetic Ratio. It's applicable to charge that is moving with an object that has inertia. So I need to limit the scope a little bit here to this loop being a solid ring of charge that's rotating with angular speed omega and thus making current little I. There are a lot of different geometries you can inspect and determine a gyromagnetic ratio, such as this toroid. I would ask you to imagine maybe a smaller cross-section. I tried to find an image of a skinnier toroid, and this is what I found. So the gyromagnetic ratio is the ratio of magnetic dipole moment to angular momentum, and we know both of those for, say, a rotating ring of charge. First, let's look at the angular momentum. It's just I omega, where I is the moment of inertia, and omega is the angular speed. And the dipole moment is current times area. I'll break down the moment of inertia, I, it's mr squared for a toroid. This is why I'm saying imagine maybe a skinny toroid. So this is accurate, mr squared. And you can replace A with pi r squared. Again, we're imagining a skinny toroid. And the current, I, is the current that's generated by charge rotating around. So it's the total charge in the ring divided by the time it takes to go around once, the period, is the current. And so Q times omega over 2 pi is I, the current. So you have a lot of things you can cancel here. Go ahead and do that, and you're left with a gyromagnetic ratio of the total charge in the torus divided by twice its mass, with m being the mass of the torus. One thing I'd point out is what's not in that expression. Dynamic variables are not in the expression, like omega. It's independent of that. And interestingly, it's independent of the size of the torus. That is, it's independent of r. As long as Q and M are right, then everything that needs to be known is incorporated into this calculation. Other geometries, like a sphere, can be surmised by dividing it up into many toroids. So that's what I'm going to do here. I have many tori. Here I'm just showing one. And again, imagine a bunch of very skinny tori, so that you have maybe a billion skinny tori making up this sphere, and they all have different sizes, and they're all filling in the space in the sphere, but they all have a known gyromagnetic ratio. So by dividing the sphere into tori of equal charge and mass, because we do have to go on the assumption that charge and mass are uniformly distributed throughout here. With that assumption, you can just say every toroid has the same charge, I'll call it delta Q, and imagine the limit as that delta Q goes to almost nothing, and each toroid has the same mass, called delta M, also very, very small. Then the gyromagnetic ratio for the sphere is the magnetic dipole moment divided by the angular momentum, and we can write up the magnetic dipole moment for each one of these toroids, and we can write down the angular momentum for each one of these toroids. We've already contemplated the magnetic dipole moment of a toroid. We have the charge divided by the period times the area that threads through it. The angular momentum of a toroid is mr squared times omega. That is moment of inertia. And the mass of each toroid is delta M, and its radius is r sub I. Every toroid's got a different radius. And omega. There are some things you can pull out because we were careful to divide the sphere into tori of equal charge and mass. So these delta Q's and delta M's are constants. You pull those out, cancel the other constants like omega and pi. You're left with sum of r sub I squared over all the tori. So you cancel these sums, and you're just left with the gyromagnetic ratio is the amount of charge in one individual toroid divided by twice the mass of one individual toroid. But since every toroid is identical, that ratio of charge and mass, that delta Q over delta M, is equal to the ratio of two toroids charge over mass. It's equal to the ratio of three toroids charge over mass. It's equal to the ratio of the entire sphere's charge divided by the entire sphere's mass. And that's what Q and M are. They are the charge of the sphere, and M is the mass of the sphere. So the gyromagnetic ratio expression doesn't change. It's the same for a sphere, same for a toroid. Now, why is this important? Well, a sphere gets us towards thinking about what an electron must look like when it's spinning. So we'll talk about two different scenarios. One is an electron that is rotating. There are only two reasons that ever happens. One, because it's in some kind of cyclotron resonance, but we're going to consider also, and more importantly, there is a nucleus in the center, which is not so material because for the moment we're looking at the electron. So you have this electron going in a circle of some radius, probably going to call it r, and it's rotating with an angular frequency of omega. Now, because the electron is negatively charged, its angular momentum vector and magnetic dipole moment vector will point in opposite directions. And the gyromagnetic ratio, being charge over twice the mass, then is minus E over twice the mass. By the definition of what gyromagnetic ratio is, magnetic dipole moment over angular momentum, then we can surmise that the magnetic dipole moment of this revolving electron must be minus E over 2m times its angular momentum. I put the subscript L's on everything, including the gamma for gyromagnetic ratio, to indicate I'm talking about orbital angular momentum. So this is the orbital angular momentum gyromagnetic ratio of an electron, as opposed to the spin gyromagnetic ratio of an electron, because spin is also angular momentum. The odd thing about it is we already concluded that the gyromagnetic ratio of a rotating sphere is charge over twice the mass, but what's known about the electron is that its gyromagnetic ratio due to spin, gamma sub s, is charge over the mass, no 2. And we'll talk about that in a minute here. A consequence of that is that the magnetic dipole moment of an electron is minus E over m sub b, the gyromagnetic ratio times the angular momentum, which now is the spin angular momentum s. So about the missing factor of 2, why does an electron have a spin gyromagnetic ratio that is twice as large as what is expected from that albeit classical consideration I had just given you? It started in 1928 with the Dirac equation, where Dirac found that his equation, which looks similar to the Schrödinger equation but accounts for the special relativistic effect of a moving electron, which is why Dirac worked on this, he found that it works if the gyromagnetic ratio for the electron is twice what is expected from a classical model. In 1948, Schwinger made use of QED to introduce corrections for virtual photon coupling, where that 2 became very close to 2, but something slightly different. And my favorite result came from 2006, where Jerry Gabriels from Harvard measured the ratio of mu sub s m sub e over minus es. You should expect to get 1 for that, based on this expression. But with all of these corrections, it's slightly different than 1. And he got 1.0011596521808576. You can already see it behind this annoying thing that's always there. That 76 reflects 0.76 parts per trillion in this correction to this being exactly 1. Next to the fine structure constant, it's one of the most precisely measured constants in all of physics. I'm kind of pleased by this being the result because Jerry Gabriels is a fellow alum of mine from my undergraduate alma mater. All of these are findings, in fact, including the Dirac equation, where Dirac simply found that this works if the gyromagnetic ratio is twice as big as what you expect. None of it really explains why the electron's gyromagnetic ratio is roughly 2 times too big, even though it can be very precisely predicted with quantum electrodynamics. But that still doesn't get us to the why. And so there's a lot of room for some philosophical treatment of it. And so Charles Sabins made an interesting comment in an unpublished essay from a couple of years ago that the gyromagnetic ratio is twice because the charge in an electron is actually rotating twice as fast as the mass. Now that actually solves another imponderable problem, which is how an electron can have as much magnetic dipole moment as it has, because in order to do so, it actually needs to be spinning faster than the speed of light. And this actually addresses that question. As you can see, this is an open question of research right now in foundations of quantum mechanics. Why does the electron have this gyromagnetic ratio? I just need to break for a moment and define another term that you need to know, and it's going to come up, and that's the Bohr Magneton. If the spin magnetic dipole moment, we'll say of an electron, is all these things, so all of these are correct statements, and mu sub s is the magnetic dipole moment due to a spinning electron. This is not a consideration of orbital at the moment. And it's the spin gyromagnetic moment times the spin angular momentum. For gamma sub s, we'll use minus e over m sub e. For the spin angular momentum, we can use h bar over 2 times the Pauli spin operator, which is a vector that points in the same direction as spin, but has this h bar over 2 in front of it. Sigma very simply has 1's, i's, and 0's in it. These 4 constants, 2 is a constant, minus EH bar over 2 mass of electron go together to make something called the Bohr Magneton, which technically is the electron's magnetic dipole moment. And then one final rendition of this whole statement is if you replace the Pauli spin operator again with 2 over h bar times the spin angular momentum, you have finding this version of mu sub s. So these are all valid versions of mu sub s. And we can pull some equivalencies out of here. For example, if you compare the second term and the last term, you can conclude that the Bohr Magneton mu sub b is minus gamma sub s, bring over the h into 2, h over 2. But if you replace the gamma with e over m sub e, you can also say the Bohr Magneton is e h bar over 2 m sub e. Any way you put it, it has this value. And I'll express it in SI units. I put this other version of it down here to bring your attention something you might need to know about when you get to grad school, and that is Gaussian units. Our textbook is in SI units, but there's no rule that says all quantum mechanics textbooks are written in SI units. You will very likely in next course be confronted with Gaussian units, which are essentially CGS units. Certain physical constants are set equal to 1, and CGS units are used, so we have ergs instead of joules. But we're going to stick with SI. There's more to life than electrons. If you have an atom, you have several electrons and a nucleus. And the gyromagnetic ratio will be a mixture of the spin and the orbital angular momentum of everything, right? You have an electron that's got its own spin and it's orbiting. Both things are going on. And so you're going to have a gyromagnetic ratio. That's the combination of those two. And it's not going to be simply one plus the other. There will be some complexity of figuring this out. So we'll summarize it with a new constant called the Lande G factor. The magnetic dipole moment is related to the total angular momentum of the electron by this Lande G factor G times the orbital gyromagnetic ratio, or otherwise written as this Lande G factor times the Bohr Magneton over h bar. If you're just talking about the spin of the electron, this Lande G factor is 2. If you're just talking about the orbital angular momentum of the electron, this Lande G factor is 1. More frequently, you've got both going on, and so you're going to want to talk about both, and the actual Lande G factor will be a combination of this 1 and this 2, and it'll be something in between. In the case of the nucleus, you also have a Lande G factor. The gyromagnetic moment of a proton is e over twice the mass of the proton. The nucleus then will have a magnetic dipole moment that is equal to a Lande G factor that is just for the nucleus times this ratio times the nuclear spin. And typically capital I is used for nuclear spin. Sorry, I've already used capital I for moment of inertia. Now it's nuclear spin. So it's spin. I could call it big S sub n, but nobody does. It's called I. That's the practice. We're going to come back to the Lande G factor. When we get to perturbation theory and we want to treat the Zeeman effect, we're going to have to calculate it. So later we are going to actually derive the expression for the Lande G factor and then use it. Let me do, as an example, a consequence of putting an electron with spin into a magnetic field. Just an electron. So a spin 1/2 particle. And the magnetic field is in the z direction. The initial state of this electron is the state that describes S sub x up. So in other words, this is the initial state of the electron. We'll call it chi of 0 of time equals 0. 1 over root 2 times the vector 1, 1. That's the spinner for S sub x up. That's our initial state. And I want to find the time development of that state. To do that, you use the time-dependent Schrodinger equation. So IH bar d by dt of the state, chi, is the Hamiltonian times chi. And when a magnetic dipole moment is placed in a magnetic field, the Hamiltonian is that potential energy. So that's what we use for the Hamiltonian, and we operate with that on the spinner. Now I can replace the magnetic dipole moment mu with the Bohr Magneton times the Pauli spin operator. And B is in the z direction, so when you dot it with the vector formed by the Pauli spin matrices, you simply get the z Pauli spin matrix. So B sub 0 times z. So that's the Hamiltonian, mu sub B, B sub 0 times sigma sub z, for an electron that is in this magnetic field. Inserting in vectors then gives us something to evaluate. Replacing chi with a b vector and chi dot with the a dot b dot vector. We still have the IH bar there, and the Hamiltonian is mu sub b times b0 times a z Pauli spin matrix, which is given here. Evaluate this to get two equations and two unknowns. You have a dot, bring the IH bar over, you have mu sub b b0 over IH bar times a. Brought the I upstairs. And the same for b dot. Make sure you see these two expressions coming out of this 2×1 vector equation. And we have initial conditions. That's this chi of 0. So with a solution, apply the initial condition at time equals 0. Each of these have to be 1 over root 2. So now we know what a sub 0 and b sub 0 are. So you have that expression for a and b. So now we can write the chi of t vector as a 2×1 vector formed by this top element and formed by this bottom element. Now that I know the spin wave function, I want to find the expectation values for S in the x, y, and z direction. So first in the x direction. To do that, you evaluate the Hermitian adjoint of the wave function times the operator times the wave function. And remember, in spin, there's truly nothing to integrate. because there's no geometrical component in these spin expressions. So what would you integrate over? Just evaluate the matrix equation. This is the Hermitian adjoint. Turn it sideways and you take the complex conjugates, and that's S sub x. I put the h bar over 2 inside, and that's the vector, and so you evaluate it and you get this. I will let you evaluate these three things and conclude, oh yeah, it's cosine of 2 times the Bohr Magneton over h bar times the magnetic field times time. And if you do the same with y, you'll get the same thing, only sine. And if you do the same thing using the z polyspin matrix in there, you will get 0. That doesn't mean that there is no spin angular momentum in the z direction. Not at all. That just means its expectation value is 0. In fact, its uncertainty is pretty big, just as likely to be something positive as something negative. These cosines and sines, being periodic functions, they have an omega inside of them, right? So I have cosine of omega t, and so there's an omega, 2 Bohr Magneton over h bar times b. It's called the Larmor precession frequency, which begs the question, exactly how is precession happening? So you have a coordinate system, and let's draw the spin vector. Now, one thing I can say about the spin vector is that its x and y components are oscillating together. One is getting bigger at the same time the other is getting smaller. I mean, you see that in the result. They're cosinusoidal. And so this spin vector is constantly orbiting around the z-axis, going around and around, making some angle with the z-axis. I expect that in general, this s vector is in the xy plane because the expectation value of z is 0. So I really can't say what this angle is. It can be a whole range of values. On average, it's going to be 90 degrees. And this spin is rotating around the z-axis. So the magnetic field is going in the z direction. By virtue of the magnetic field being in the z direction, the spin is going to precess around the z-axis. And that's precession. And the frequency at which it precesses is the Larmor precession frequency, which some of you have already seen if you've done the NMR experiment in advanced lab, or when you do the NMR experiment in advanced lab. I sure hope you do. You will come across Larmor precession then and analyzing those results. Next time, maybe I'll be able to talk to you a little bit about the Stern-Gerlach experiment.